Hello, everyone. Welcome to this next session where I talk about autonomous optimization and cutting serverless latency by up to 50%. I'm Nikhil Gopinath. I'm the VP of Engineering for ML platforms at Sedai, and I also work mostly on the serverless side of autonomous management. Joining me on this call was supposed to be Avinash Gupta, who is a senior site reliability engineer at Fabric. Unfortunately, due to a last-minute emergency, he might not be able to join us. He is still trying to, but if he doesn't, I will cover some of the slides he was planning to talk about. So I apologize for that. So yeah, let's get started. So go to the next slide. So what we're going to cover in this session is some optimization challenges. As an organization grows, or for that matter, any system that grows, right? As complexity increases in a system, it also starts to collect some inefficiencies and unoptimized areas. This is true for any system, right? For a business, for an organization, for living organisms, for computer systems, and so on, right? So it becomes important that as your business grows and the underlying infrastructure that drives your business grows, you try to find those inefficiencies and keep them optimized. And that's one of the challenges of optimization that we're going to talk about in this particular session. We'll see how Sedai helps in optimizing serverless functions, focusing particularly on Lambda and a few niche areas within that. And then the second part of the talk is about how Fabric saw a reduction in latency by up to 50% by using some of the solutions that Sedai provided them. So the optimization challenge, let's contextualize this. Let's understand what the challenge here is. So the context here is we are talking about Lambdas. And in Lambdas, the objective here is, the objective of Sedai in general is to make sure that everything is performant and available and optimized, right? So that's kind of how we manage the life cycle of every resource that we touch. We want to make sure it's up and available, and it's performant and performing as optimally as possible. So in the context of Lambda, when you want to control the Lambda, here are some of the things or the knobs that you can tweak. So you have memory settings. So that's one of the configuration settings out of the box in AWS, right? You can increase the amount of memory, and that leads to a bunch of things. And that's what we're going to focus on in this session, primarily on memory. But just for completeness, the other things you could tweak is provision concurrency, right? So you can autonomously increase concurrency by managing that. There is the concept of reserve concurrency in Lambda to manage throttles and thresholds. You can manage timeouts for Lambda as a way to kind of make sure everything the operation runs the way you expect it to. And outside of what AWS offers, you also have the concept of warm-ups, which some of you might be doing through warm-up plugins or other third-party solutions. In a subsequent talk later today afternoon, we'll see another solution that Sedai offers to kind of overcome those limitations. But in this call, we are going to talk about memory settings. So memory. So let's look at this graph a little carefully, right? You can see that you can, for any AWS Lambda, you can set the memory from 128 MB, that's the minimum that you can set for any Lambda, all the way up to 10 gigs. And you can linearly increase it by increments of 1 MB at a time, right? Now, what happens when you increase memory, right? Obviously, you get more RAM, right? And so you get all the advantages of additional memory. But what AWS has done very smartly behind the scene is it also abstracts the concept of CPU and the processing horsepower behind the memory setting, right? So every time you increase memory, you also get an additional fractional CPU that's added to your Lambda, right? So if you increase memory from 128 MB to, let's say, 256, you see a corresponding increase in amount of processing horsepower that your particular Lambda gets. And they're tightly coupled, right? What you see is this relationship between memory and CPU is pretty linear. You increase one, the other one increases, and it's a straight line, right? Very simple, nothing hard, nothing complex to understand so far. Things get a little bit more interesting when we talk about the CPU cores. Now there are very preset points in this graph where the number of cores that's available to your Lambda jumps from, let's say, 2 to 3 and 3 to 4 and so on. So this is well documented. This is a known behavior and something that AWS lets you take advantage of, right? So as a developer who's writing Lambdas, this is something that you have to pay a little bit more attention to, right? So you want to make sure the Lambda that you run is able to take advantage of all the cores, right? So you select your choice of language that you use for the Lambda, your choice of libraries, make sure that they can take advantage of all the CPU cores and at all these memory set points as you increase the configuration of memory. So that's pretty simple. Memory and CPU are directly related, and increase one, you increase the other. Now let's look at the execution duration. What happens when you increase memory? How does your Lambda perform? Now this gets interesting, right? So if you take any computational unit, a function, a web service, anything, right? There's two parts to it. There's a fixed part and there's a CPU dependent part. So the fixed part of this is usually like the time taken for you to make a round trip call through the network, right? So you may be invoking a third-party API or some other API. You might be accessing storage. You might be making database calls. So these are all independent of how much horsepower you have, right? Even if you double the CPU or maybe even double the RAM, this fixed part remains the same. Right? So that's the baseline part of your cost for running that particular service or Lambda or function. And then there is a CPU dependent part. This is the part that changes when you add more CPU, when you add more horsepower, right? This could be because of some algorithm, which might be repeatedly, recursively looking at your data and doing some processing, right? Typical for a lot of algorithms, machine learning use cases, and so on. Or you might be doing data crunching, right? You might be aggregating some data in memory, and the more memory and more CPU you have, the better it performs. Or you might be doing something like image processing or video processing, which are again very CPU and horsepower dependent. So that's the second part of this equation, right? So now if you plot the dependency between memory and CPU and the execution duration, this is sort of the curve that you get, right? It's not linear at this point, right? The relationship between them is not that, I mean, it's not very intuitive why it is, but if you think a little bit more about it, you know that more CPU you add, it doesn't necessarily mean you double the performance, right? There's a point of diminishing returns. So that's what we reflect in this curve here, right? And here, again, just to reiterate the point, as you increase memory, you are increasing CPU, and which in turn is what is affecting this particular distribution. So there is the point here is there's a non-linear relationship between memory and duration. And memory, in turn, indirectly means also CPU. Now let's look at another thing here, right? Let's look at cost. How does memory impact cost? So if you look at the documented way of for pricing on Lambdas, you see there is two components to it. There is the duration part of it, that is the amount of time that you're actually running the Lambda or using AWS's resources for, and the settings that you set there, right? The memory, right? So both have an impact on cost, right? The duration and the memory. So now this becomes a little bit more complex. It's not a linear relationship anymore, and it's not even a smooth relationship, right? It's kind of like a U-shaped convex relationship. What you see here and from this graph here is as you increase memory, initially the cost starts decreasing, and then it starts to go up, right? And that's a convex relationship between memory and cost. And why is that? Like I said, part of the cost is dependent on memory, and the other part of it is on duration. And as we already established, the relationship between memory and duration is not linear. It's a complex relationship, and that actually compounds this problem here, and we get a non-linear relationship between memory and cost. So now if you can define our optimization problem, the problem here is you want to control, you have whatever controls you have, you want to optimize for performance and or cost, right? You might be a customer who care about performance, you might be a customer who care about cost, and we'll see those differences, nuances in a little bit, but that is the definition of the problem, right? Now for folks who have worked on algorithms or control systems, you know that this is a convex optimization problem, and you have multiple objectives here. So you define your objective function using performance and cost, and then try to control the independent variable to get the best optimum performance and cost, or whatever goals you set for it. So let's see what that looks like, right? So now in this particular graph, I have gotten rid of memory, right, which is the control you have, but introduced both the optimization targets. You are optimizing on duration on one axis and cost on the other axis. Right? So if you look at this, and if you try to understand this graph, what you're seeing here is, again, the non-linear relationship between duration and cost. Now, having observed a bunch of Lambdas in a bunch of customer environments and many places, what we come to realize is that by default, right, it's very hard to understand what should be your setting so that you get a certain amount of performance or a certain amount of cost, right? So or pay a certain amount of cost. So this shaded area in this picture is where most customers and most Lambdas we have typically found to be. So what it means is that if you look at the horizontal x-axis, we are talking about duration, right? So it's towards the right. It's not towards the left where you have the best performance. You are skewed towards the right where your performance is not as good as it can be, right? And if you look at the y-axis here, you can see that this is again not at the bottom of the curve. It's not the best cost you can, right? So typically by default, customers are having configured their Lambdas to get the best duration or to get the best best cost, right? So that's the state of the default settings in most environments. What do you want actually, right? I mean, what would a default best of both worlds situation be? So that would be on the bottom left corner of this graph. So where you have the lowest possible duration and at the lowest possible cost. So this is a no-brainer, right? Why should you pay more to get a certain amount of performance if you can get the same amount of performance at a lower cost, right? Or you can flip the argument the other way around, right? Why should you pay a different amount, right, if you can get the same performance? I mean, why should you pay a higher amount if you can get the same performance at a different cost, right? So that's the default optimization target that we target for, right? We try to do in Sedai. So on the left side here, what you see is one of the control panel within Sedai, right? This is where by default, if you are onboarded onto Sedai as a customer and we are managing the Lambdas for you, by default, we'll try to get you the best of both worlds. We keep the same cost, and at that cost, what is the best duration? What's the best performance you can get? And that is the shaded area that you see in this picture. Now, moving on to real-time use cases, right? So a lot of our customers, and we'll see a little bit of this when we talk about Fabric in the second part of this talk. A lot of customers care about real-time end-user performance. Maybe you have a shopping cart, or you're checking out something from an e-commerce website, or someone is logging in and trying to make a payment, right? Those are all scenarios of real-time use cases where you do not want a hiccup. You want the best possible performance at the best possible and the best possible experience to your users. You do not want a failed customer interaction at that point, right? So in those cases, our customers are willing to invest a little bit more money and say that I don't care about how much more that you spend a little bit more, right? But give me the best possible performance for this set of functions or these Lambdas. And that's one of the settings that you have here on Sedai on the left here, where we say, well, let's increase the performance, improve the performance, right? Decrease the duration, even though that might be incur a little bit additional cost. So here they said like 25%, charge us, spend 25% more on this Lambda. It's okay to do that as long as you improve the performance here. And that's where the shaded part in this chart shows up, right? So this is where you have you can see that the duration is trending towards the left, right? So you're running faster and faster, but you're willing to pay a little bit more on cost, right? But you don't want to go all the way here, right? Because there's no huge difference between performance at this point versus this point, right? Although the cost is pretty steep as you go up this way, right? So you want to stay somewhere in the bottom part of this curve. Now, one thing I actually did not actually clarify or mention very clearly is this is the relationship for what I'm showing here is for a sample Lambda. But this is the kind of complex relationship you will find between cost and duration for any Lambda that you write, right? Now, the actual shape and the nature of the graph depends on your particular Lambda, on your particular implementation, on the function and everything that happens behind the scene. What Sedai does is we introspect your Lambda, we understand its performance characteristics, its memory characteristics, its cost characteristics, and plot this graph for every single Lambda that you work on. And then based on your requirement, your goal, right, whatever you tell us to do for the Lambda, we find that sweet spot within this entire graph and then optimize the Lambda and bring it to that sweet spot. So reiterating here, for real-time use cases, you want the best duration possible, even though it might cost you a little bit more. And that's what you're telling us through the setting here. And that's what we try to achieve. Now, let's go to the other side, right? You have a few backend processes that's crunching numbers, maybe downscaling an image from whatever user uploaded to show on the profile picture. No one is actually sitting there waiting for the profile picture to show up the first time you upload it, right? Or even if you do, it's okay to be a little, for it to take a few more seconds, right? Because those are not like real-time use cases where someone is actually waiting for it or you don't care. Or there's a bunch of other scenarios, right? For batch processing, like end of the day data processing or end of the month reporting, right? These are all happening at either downtimes or behind the scenes and producing something as the output, which eventually gets available to the end user. So bottom line here is it's not performant or duration sensitive. It's but at the same time, it could be cost sensitive, right? Because you might be doing a lot of this in the backend. So in those kind of scenarios, you want to get the best possible cost, even though it might take a little longer, right? So that is the optimization we target in this particular scenario, where you decrease the cost, but again, you want to put some limits on the time it takes, right? So here you're saying, well, decrease the cost, but don't increase the duration by more than 25%. So you still want to cap it to a certain extent, right? You don't want it to just run wild and take forever to get the output of that batch process. So that's the setting here, and that's the optimization that you can target in this particular case. Now, moving on, right? So essentially, this consolidated picture actually shows you all the possible optimization targets you can have for a Lambda. And again, like I said, this graph, the shape of the graph is very unique to every Lambda. And the challenge here and the most interesting problem to solve here is, how do you find that sweet spot? Now, you as a customer would tell us what your objective is, but how do we find that sweet spot on this graph? That's where Sedai comes in. Now, let's take that problem, now that we understood what the problem is and what the objective is. Let's look at behind the scene, what are the complexities that make it even more interesting. So there are a lot of a lot of variables that come into picture, right? Like I said, each Lambda is unique. It's not just unique in its implementation, it's also unique in its traffic patterns. It's unique in its the duration it takes, right? Every Lambda will have a mean duration and a spread of its duration in terms of what the standard deviation of that would be, and that spread is different for every Lambda. Traffic pattern likewise will be very different, and the dependencies that it may have, right? A certain Lambda might make just one backend call, some may not make any backend calls, some might be making multiple calls. So all this makes for very interesting modeling problems for us to find out the shape of that cost versus duration relationship. External changes, right? While we are tweaking the Lambda and optimizing it, well, a customer could go onto the AWS console and make some changes there, right? So these are changes outside of our control on the configuration itself, or it could be a CI/CD process pushing something else, which also brings us to the topic of releases, right? Your developer must be continuously building or updating Lambdas, fixing bugs, adding new features. And every time a new release comes in, it changes the profile of the Lambda, right? What used to take, let's say, 100 milliseconds previously might take 120 milliseconds now for execution, right? So a lot of the characteristic that we identified from the graph, we'll have to now rework on that and revisit and understand that. So understanding that relationship is an ongoing thing, right? As things change, as environment changes, as new releases come in, you have to continuously keep doing that modeling exercise. And safety, right? You don't want optimization to ever cause a problem. It has to be always safe, and it should be repeatable, right? Anytime you something undoes a optimization, you may want to redo that optimization to get to that sweet spot. And finally, there are other complexities, right? Other externalities, like you can change the concurrency of a Lambda, right? You can change provision concurrency. You may be using warm-up calls, or like I mentioned earlier, we'll see about some other cooler ways of achieving warm-ups through autonomous concurrency later. But there are other factors that you can change within a Lambda, right? This also adds to the complexity of autonomous optimization. So how do we do this? What does it look like under the hood, right? So what we did is we modeled a life cycle based system, right? A life cycle modeling approach where we define the goal of what Sedai does in terms of optimization as a function should be available and optimized, right? So both are very important goals for Sedai and for the autonomous system. That is, the function should always work, right? You should not have a downtime, and even if it's an external reason to cause a downtime, Sedai should fix it, right? So it should be available and optimized, right? Whatever optimization goals are set to that resource, it could be set by the customer themselves, or it could be something that we set for the function based on the default configurations, right? So we uniquely identify this relationship between memory and duration, and memory and cost, and duration and cost, right? So do this for every single Lambda and find that relationship and model the Lambda. Then now that we understand the shape of that graph that I was talking about, we model a strategy to drive that function to that goal, right? So you know a goal, you know what the shape of that Lambda is. Now, through a recurrent reinforcement learning technique, we drive that Lambda, that function, towards that goal. And then we continuously monitor this process, right? You don't want to make a change and then just sit back and relax. You have to make sure that your optimization reaches the goal and stays there, and also watch out for external all the other external variables that might impact it, like the ones that I mentioned earlier. And like I said, revisit the strategy when external changes are detected. So that's sort of how the optimization process works under the hood in Sedai. So what I'll go through next is some of the slides. Avinash wanted to talk about how Sedai was able to achieve some of the goals for Fabric by reducing the latency by up to 50%. So about Fabric, briefly speaking, they are an e-commerce platform, and their customers are e-commerce vendors, right? So think of it like they provide the e-commerce platform for any sellers, right? So a seller get onboarded onto Fabric, they set up the store, and then they start selling, right? So essentially, they help their customers set up their e-commerce platforms through their offering. Now, e-commerce is very latency sensitive, right? It's very easy for customers to bounce off your homepage or off your checkout page if things takes too long, right? We are all very picky buyers when it comes to online experience. Just like any e-commerce service, it's also very seasonal and very holiday and event driven, right? You might have a promotion that might increase or change your sales and marketing outcomes, or holidays affect you very differently, right? So but there could be promotions. So there's a bunch of things that could influence the volume of traffic and the way your system needs to respond to that, right? So the system that Fabric built has to respond to those externalities and should perform at optimum performance for their end customers whenever they activate the system. So Fabric built this mostly on the serverless architecture. So they relied a lot on Lambdas to get to the initial part where they can scale up, scale down, and manage their fleet very quickly and easily. Some of these workloads are also being put into EKS and ECS to kind of balance performance and cost and optimization and many other internal targets. Very specifically, the payment service, right? The high, which is the most latency sensitive. So again, we all know this as customers, right? You want your payment thing to go through, right? You don't want a customer to get second thoughts while twiddling fingers on the payment screen, and you don't want to drop any payment transactions either. And lastly, here AWS has multiple customers. So every customer gets their own, are onboarded as on a multi-tenant environment through separate AWS accounts, right? So there is the amount of complexity in managing different customers increases obviously as their number of customers increases. So some of the challenges that they had internally for managing serverless functions, right? It's a very dynamic environment. Things change. They keep on adding more features, and they want to make sure everything is optimized and the performance is meets all the thresholds and the service level objectives. And critical needs to continuously right-size the function, make sure it's set to the right configuration in terms of memory, provision concurrency, make sure that the functions are warm and ready to act on a customer's request, right? You don't want the customer waiting with cold starts or the customer waiting on cold starts for the Lambda to warm up. And obviously, if there is a problem, you want to get to the root cause of it pretty quickly in a highly distributed environment, trace the errors and follow it through, get to the fundamental reason that triggered that problem. And do all this while keeping your costs as low as possible. So this would potentially be what any customers seek out for on Lambda and serverless, right? You want all these things and you want it to be as low cost as possible. And each stage, and then they get continuously new releases. And also very importantly, the SRE team is focused on multiple priorities, right? So they have a very small team, and they want to make sure that the focus stays laser focused on performance, but at the same time, as they get more customers, how do they scale their SRE team very efficiently and onboard more customers quicker and more efficiently? So these are some of the challenges that Fabric faced internally. This is a brief overview of what their internal architecture looks like, right? So they have a storefront, which is the heart of the e-commerce engine, and then there's a bunch of Copilot apps, right? So this is typical for any external facing system, right? You have the core business generating storefront external facing part, and then there's a bunch of things that's a supporting layer around it, right? So the core part, like cart management, ordering, shipping, identity management, these are all what a customer, right, a buyer would experience. And all other things like setting up offers, inventory management, loyalty system, image management, inventory management, all those things are behind the scene that internal operators and business would need to be aware of. So this is kind of how their system is broken down into. And then they also depend on a bunch of other external services, right? So for payments, shipping, for search, notification, etc., right? So there's a dependency chain, right? So there's a bunch of external and third-party tools and libraries and frameworks that they actually depend on as well. So setting all this up and the infrastructure behind the scene requires up to more than 10,000 services, right? A majority of them are written in serverless on Lambdas, and they are written either in Node or Python or Java, right? So there's a mix of there's a variety of languages, and there's a mix of languages that goes behind the scene in terms of what the actual implementation is. And there's a little bit of Kubernetes and serverless containers as well when it comes to completely defining what the backend environment is. So here is what I said I was able to do for Fabric, right? So this is a sample Lambda here, right? So the name obviously here is obfuscated. But for this Lambda, we were able to improve the duration by 88%, right? So and overall, right, with over a period of time, the latency reduction was down, but the latency was reduced by up to 48%, right? Now, like I said in previously, right, they wanted this latency reduction even though they are willing to spend a little bit more, right? And this little bit in this case was just $12, right? So the grand scheme of thing, you are able to almost cut your duration, your latency by half by spending just a few dollars more. So that's the magic of optimization when you look at that complex optimization problem and try to find that sweet spot, right? And again, this works for all combinations of optimization targets. In this particular case, they're trying to optimize on performance, but if you want to optimize on cost, you can get the same kind of behavior, right? So hypothetically, let's say if they wanted to optimize on cost here, you would see something like the latency remained like almost like maybe the duration went up by 5% or 10%, but you are able to reduce cost by, let's say, up to 40 to 50%. So that's the flip side of what you would have seen if you targeted the other optimization. One of the other things that we were able to work out very efficiently with Fabric using Sedai was the whole idea of scaling up and down, right? Scaling up is easy. Anyone can scale up, and adding more memory, adding more resources, it's easy, right? You run little risk. You don't run a lot of risk when you do that. But scaling down is a harder problem, right? Internally, previously when Fabric wanted to scale down, they required multiple internal approval. They needed to do a cost analysis, risk analysis, what could be the impact on performance, what could be the impact on availability, and so on. Sedai completely wipes out all those concerns from your active conscience, right? So we are able to within Sedai we have an efficient system for safety check, which dry runs every possible operation, be it a scale up or a scale down, and then efficiently decides what is the best way to execute the operation, right? So for every scale up, for every scale down, there is a safety check. If the safety check fails, well, for whatever reason, we do not continue, right? So rest assured, all the risk and the concerns you might have is already taken care of and addressed behind the scene. Then the other other things that Fabric was able to get out of this is the fact that since this is ML driven and continuously reinforced, right? So even with releases and with changes going in, they didn't have to worry about what do they need to scale up or scale down, right? So if they scaled up a Lambda, for example, right, and then now you have a more optimized code that's actually running better, right? Supposed to run better. How do you scale down, right? To what extent do you scale down? Now all that part, all that problem, all that solution is taken care of by Sedai behind the scenes. So this is just another representation of latency versus cost optimization, right? The goal here again is to define that optimal point on the curve where you get the best cost or do you get the best latency, right? In this case for Fabric, pulling down the cost is good for Fabric, right? But that's not what the customers want. Customers want speed, right? So it's always balancing between the cost and the speed, right? How much improvement do you want, and what is the cost that you're willing to spend on that? So that becomes a very easy configuration for Fabric to make and get the outcome. We talked about seasonality, and so there's a high level of seasonal variation within the data, within traffic that Fabric sees with all of their customers, right? Now, again, based on the continuous monitoring and the continuous optimization features within Sedai, we were able to keep up with all the ups and downs, right? So when traffic goes down during the middle of the night, or during weekends, or during lull periods, we are able to scale down the requirements and make it more cost efficient. And when traffic blooms during high peak shopping hours or during some other events, we are able to scale up correspondingly and get to that optimum and keep it continuously monitored. So and this comes at there's no pooling of capacity. I mean, that's one of the features of using serverless technology to begin with, right? You don't have to take resources from one place and put it somewhere else, right? That's we're able to do that efficiently, even with cost, right? Even with money on your behalf. Some of the challenges they have is has to do with cold starts, right? Now, optimizing for cost and duration doesn't necessarily eliminate cold start, but that's something we will leave for a later session today. And with that, I went through most of the slides that I want to talk about. I will open the floor now for any questions. And joining me here is Meenakshi. She's our senior software engineer who was instrumental in building a lot of these capabilities. Okay, so a question I see here is, will autonomous actions cause downtime or increase cold starts? Well, yes. So that's so one of the very key things that we wanted to be a part of the platform when we started out was it should be any action that we do should be safe, right? we should not cause any problem. So I mentioned about the safety checks that we do as a part of every action. So within every safety check, we look at historic data about what was the things that we did that actually caused an improvement in the outcome, right? And the reinforcement learning kind of helps in getting better and better at those tasks. But one of the advantages of now working with serverless and lambdas in particular is when you increase memory, right? For example, you are not touching anything that's already running, right? You are already, if a customer has already invoked a lambda and they are experiencing a execution, that still runs to completion before the new memory settings takes effect, right? So that's completely abstracted to a large extent by the AWS platform itself. So we just build on top of that and make sure that we don't do anything crazy, right? So with the safety checks and all the process that we have in place, Sedai will not lead to a problem in downtime or increased cold start because of an optimization action that we do. Yeah, the next question here is, does duration always go down when you increase memory in Lambdas? That's an interesting thing, and that's one problem that Meenakshi has always battled with. Meenakshi, if you're on, would you want to answer that?
Nikhil, yeah, sure. So, say we have a lambda that performs, CPU intensive tasks, then we can expect its duration to decrease when we increase the memory. But sometimes we see that memory has no impact on duration. So in that case, if the safety conditions are met, we can usually try decreasing the memory.
Right. Yeah. And it feels a little counterintuitive at times too, right? I mean, if your lambda is not memory or CPU intensive, right, then why do you have to allocate so much memory or CPU to it, right? Maybe all your lambda is doing is getting a request, forwarding it to another downstream processing API or endpoint, getting the request and sending it back, right? Now you don't need a lot of memory or CPU for doing that, right? So there is a potential for increasing or decreasing your cost, but keeping at the same performance level, right? So this does happen, and we have seen that a few times where duration actually is not impacted by changes in memories or lambda settings. Another question is, does this approach work for all lambdas, or are there any restrictions? What we have built here, right? So the first our first pass of the solution, we were only able to make this memory changes to latest lambdas, right? So unversion lambdas. So if you're familiar with the ecosystem, within a lambda, you cannot change memory settings once it's published, once it's already out there, right? So you have to republish it, reversion it. So in the first pass, we were not able to do that to version lambda. So we are only able to handle memory changes and optimization for unversion lambda. But eventually we added this feature where we take a version lambda, we know it has a certain memory profile and settings done. We ourselves create a new version of the lambda, right? And again, like everything else, we do this in a very optimized manner, and do all the safety checks and make sure that we publish a newer version of the lambda, which is able to now perform optimally, right? So at this point, there is no limitations. Any lambdas that you write will be able to take advantage of this solution. All right. Okay, I'll look around for any other questions. All right. Yes. So please feel free to post any questions in the chat session or in a comment section. We will be glad to get back to you even after this talk. Yeah. So with that's all. So the next session up would be moving to NoOps with autonomous and serverless with Sam Williams, and that's going to start in another 5 minutes on the dot. All right. Thank you, everyone. Thanks for attending.